Today we're going to be talking about section 2.2, the inverse of a matrix. So in the last video, we talked about a number of arithmetic operations we could do on a matrix. So we talked about sums, we talked about multiplication of a couple different varieties. What we didn't talk about was division. And it turns out that the reason we didn't talk about this is that division is a little bit nuanced in terms of matrices. But before we get into how to quote unquote divide a matrix, let's take a look at what we mean by division in general. So if I have the number 5 and I want to get it down to 1, I would multiply this by 1/5, and this would get it down to 1. So you could think of this as dividing by 5, but you could also think about it as multiplying by 1/5. This number is called the inverse of 5 because it undoes what 5 has done, right? So if we multiply by something by 5, we can undo that by dividing by 5 or conversely multiplying by 1/5. This is the idea that we're going to use when we're talking about matrix quote unquote division. Instead, we're going to think of finding an inverse of a matrix and then doing matrix multiplication with that inverse. This is really helpful because we already know how to do matrix multiplication, so we don't need to find some kind of new convoluted thing for how to divide matrices. If we can find an inverse for that matrix, then we can multiply those together and that will undo the matrix, so to speak. All right, so let's talk about what an inverse actually means in terms of matrices. So, well, let's start with this definition of what it means to be invertible. An n by n matrix A is invertible if there exists an n by n matrix C such that when you multiply them together, you get the identity matrix. The matrix C is called an inverse of A and is in fact unique, and we denote it as A inverse. So that's A raised to the -1. So a couple things to note about this definition. First of all, the definition isn't really centered around inverse, it's centered around the word invertible. What this tells us is not every matrix is invertible. Not every matrix has an inverse. In fact, right off the bat, we can note that only square matrices even have the potential to have an inverse. And not every square matrix does. So if our matrix has an inverse, then we can multiply the inverse by the matrix to get the identity. This is like what we did up here where we multiplied 5 by its inverse to get back to 1. 1 is sort of our neutral safe space, and the identity is our matrix version of 1. All right, we looked in the last video that if we have AB equals AC, we can't necessarily say that B equals C, right? This was what we said, cancellation doesn't work. We can't necessarily quote unquote divide by A. However, if A is invertible, then we have an inverse for A. So then we could multiply both sides by A inverse. And then because matrix multiplication is associative, we saw this in the last video, we can redistribute those parentheses so that we multiply A inverse by A first. What happens when we multiply something by its inverse? We get the identity. And we saw in the last video that the identity times the matrix just gives you the matrix back again. So if A is invertible and we have AB equals AC, we can in fact conclude that B equals to C. So this is the power of an inverse, is we can effectively undo a matrix multiplication. Great, so we've seen why we like inverses. Now, how can we tell if a matrix has an inverse, and how can we find what it is? That's what we'll be talking about for the rest of the video. Let's start off with 2 by 2 matrices. We have a convenient formula for 2 by 2 matrices. So let's let A be this square matrix, and let's call the top entry A, the other top entry B, C, and D. So let's say A looks like this 2 by 2 matrix. Then what do we have if A times D minus B times C, so that's the diagonal entries minus the off diagonal entries, A times D minus B times C. If this does not equal to 0, then A is invertible. So this is really easy to check with a 2 by 2. You just take that product and say, is that true? Then A is invertible. And in fact, we can even find the inverse. So A is invertible, and the inverse is going to equal 1 over that product that we just took, times, we're going to switch the on-diagonal entries and negate the off-diagonal entries. So here's our formula for finding the inverse. On the other hand, if AD minus BC equals 0, then A isn't invertible. So this is really easy to check and pretty easy to get the inverse as well. Incidentally, this AD minus BC is called the determinant of A. We'll talk a lot more about determinants after spring break. Okay. So this also makes sense, right? If this thing is equal to 0, then if we tried to do the inverse formula, we would be dividing by 0, which is impossible. So that's why that 0 stipulation is there. Let's take a look at an example. So let's say A equals to 3, 4, 5, 6. All right, we want to know if A is invertible, and if so, what its inverse is. So our first step is we want to take the product of the on-diagonal entries and subtract it the product of the off-diagonal entries. So 3 times 6 minus 4 times 5. This will give us 18 minus 20, which is -2, which notably is not 0. So A is invertible. If we want to find the inverse, what do? We'll say A inverse equals 1 over that number that we just found, 1 over that determinant, times we swap the on-diagonal entries and we negate the off-diagonal entries. So here is our inverse. If we want this just as a matrix, we can do scalar multiplication like we talked about in the last video. Just distribute that -1/2 through to get -3, 2, 5 halves, and -3 halves. So here is our inverse. And you can check that if you multiply this matrix times 3, 4, 5, 6, you will get the identity matrix and vice versa. All right. So that's how you find the inverse from a 2 by 2 matrix. Before we talk about how to find inverses with bigger matrices, let's talk about just a couple of properties to make sure we know how to handle some of these inverse matrices. So let's take a look at our properties. Our first property is that if A is an invertible matrix, then so is A inverse. And in fact, the inverse of A inverse is going to be A. This shouldn't be too surprising because what does it mean to be an inverse? It means that if you multiply them together, you get the identity, right? So the thing that we would multiply A inverse by to get the identity is A. Our second one is if A and B are both invertible matrices, then so is their product. And in fact, if we want to find the inverse for that, then that is going to be the product of their inverses. Something to notice here is that when we quote unquote distribute that inverse through, we have to multiply by B first. This is called the socks and shoes principle. Imagine that A is socks and B is shoes. If you put on your socks and then you put on your shoes, if you want to undo that, you have to take your shoes off first and then take your socks off. You have to do it in the opposite order. Our last one is if A is an invertible matrix, then so is A transpose. We talked about transposes in the last video. And the inverse of A transpose equals to the transpose of A inverse. So that's pretty easy to find as well. Okay, so these are our properties. Now let's take a look at how we might find an inverse of a larger matrix. Before we do that, I want to introduce some definitions, and it'll become clear why this is important in a second. So we've been talking over the last unit about elementary row operations. Any elementary row operation on a matrix can be written as E times A, where E is the square matrix created by performing that row operation on the identity. This is called an elementary matrix. All right, that's a lot of words, but it's not actually too hard to do. let's take a look at an example. Let's say our A equals 1, 2, 3, 4, 5, 6, 7, 8, 9. And let's say we want to do a row operation that is scaling the second row by 3. Let's say we want to multiply that second row by 3. So we could just do that. That's what we've been doing in the last unit, or we can think of this in terms of matrix multiplication. So what this elementary matrix is saying is if we take the identity matrix and we do that row operation that we want to do on our A on the identity matrix instead, then this gives us 1, 0, 0, 0, 3, 0, 0, 0, 1. This is our elementary matrix E. And if you multiply E times A, and you can double check this on your own, what will you get? You'll get the matrix that you would have gotten if you did that row operation directly on A. So this would be 6, 15, 24. We're just multiplying that second row by 3, and 3, 6, 9. So we're reframing our elementary row operation as matrix multiplication, where we're multiplying that matrix A by an elementary matrix. If we want another example, let's say instead we wanted to do row replacement. So let's say we wanted to take row 3 of A and replace it with row 3 minus 3 copies of row 1. Then again, we would look at our identity matrix and then do that row operation on the identity matrix to get, well, the first 2 rows are exactly the same, but if we do the row operation on the third row, we'd get minus 3, 0, 1. So this is our row replacement elementary matrix. I'll call this E1. And if you do E1 times A, you'll get the matrix A, but doing that row replacement on that third row. So these are elementary matrices. And why are we introducing these? Why do we care? Well, it turns out that elementary matrices are useful because every elementary matrix is invertible. So if we take a look at what that looks like, I'm just writing this down, but this just saying every elementary matrix is invertible, and its inverse is really easy to find. It's just what would bring it back to the identity matrix. So for instance, how do we undo scaling? Well, if we multiply the second row by 3, we can get the inverse by dividing by 3, right? This is really easy to undo. So this would be our inverse. Okay, and how would we undo subtracting 3 copies of the first row? We would add 3 copies of the first row. So if we wanted the inverse of this one, we would have 1, 0, 0, 0, 1, 0, and positive 3, 0, 1. So these are pretty easy to find the inverses of. Okay, again, why do we care? Well, we care about this because if we can get A via elementary row operations down to the identity matrix, then we can also get A via elementary matrix multiplication down to the identity matrix. So say we did, I don't know, K row operations on A to get it down to the identity matrix. I can think of this as multiplying by a product of several elementary matrices. This is going to be A inverse. So A will be invertible, and the inverse is going to be the product of elementary matrices. And the fact that those elementary matrices have easy to find inverses means that not only can we tell that A is invertible, we can also find the inverses by taking a look at the elementary row operations that we did to get there. So to recap, let me just write this down so that you can see it. So if our matrix is invertible, then A is going to be row equivalent to I. So that means I can get A down to the identity using row operations. And in this case, the sequence of row operations that reduces A to the identity, also that exact same sequence of row operations would take the identity to A inverse. Okay, so the last few minutes that we've been talking about elementary matrices may have seemed complicated, but it is all leading up to a really easy algorithm to find the inverse of a matrix if it's invertible. So here's our algorithm. So our algorithm is we're going to take our matrix A and augment on the identity matrix. And then if we do row operations and can get A down to the identity matrix, then A is invertible. And that reduced augmented matrix will give us A inverse in the augmented side. If we don't get the identity matrix here, then A isn't invertible. Okay, let's take a look at what this looks like. So this is our algorithm for how to find an inverse for a matrix that is larger than 2 by 2. So let's look at this. Let me just re-put our algorithm here so that we know what we're trying to accomplish. So again, this will give us A inverse. So let's say we want to tell if this matrix, so here A will be 0, 1, 1, 1, 0, 3, and 4, negative 3, 8. We want to know two things. One, is this matrix invertible? And two, what is its inverse if it is invertible? What do? Well, the first thing we do, our first step in this algorithm, is to append on or augment on the identity matrix that's the right size. So we take this matrix and we just augment on the identity. Okay. Then we row reduce and see if this side can reduce down to the identity. If it can, the matrix is invertible, and if it can't, then the matrix isn't invertible. So let's give this a shot. This is great because it again uses our row reduction tools that we have learned in the past unit. So the first thing we want to do is we'll notice that our one that we want in the upper left corner is in the second row. So we'll go ahead and start by swapping those two rows. So our first row will become 1, 0, 3, and we also want to carry with us the identity matrix on the other side. All right. Then the next thing we're going to want to do is we already have a 0 underneath of our 1, so let's get rid of the 4 here. We'll also notice that we want to get rid of this -3, and the first row has a 0 there, so that's not going to disrupt it. So let's actually do both of those at the same time. So we want to take row 3 and we want to replace it by row 3 minus 4 copies of row 1 plus 3 copies of row 2. Okay. So what will that look like? Well, our first two rows stay exactly the same, and the row also stays exactly the same. And then our last row, we're getting rid of the 4 by subtracting 4 copies of row 1. We're getting rid of the 3 by subtracting or adding 3 copies of row 2. And then what do we get here? This is going to be a -1. We can see this by saying, okay, we took the 8 from row 3. We subtracted 4 copies of row 1, which has a 3 in that spot. And we added 3 copies of row 2, which has a 1 in that spot. So 8 minus 12 is -4, plus 3 is -1. And then again, we carry through. So we're adding 3 copies of row 2. So this will be a 3. We're subtracting 4 copies of row 1. And this one stays the same. We can do this pretty easily because we had zeros everywhere else. All right. Now what do? We have a couple of more operations to do. I'm going to give myself a little extra room by erasing this. But we can sort of do them all in one fell swoop. So what do we need to do to row 1? We need to get rid of this 3. So we'll take row 1 and we'll replace it by row 1 plus 3 copies of row 3. And then for row 2, we want to get rid of that 1. So we'll take row 2 and we'll add row 3 to it. And then finally, for row 3, we will scale by -1. So if we do all of these, this isn't anything new, by the way. Okay, so we're adding 3 copies of row 3. So we've got 9 plus 0, minus 12 plus 1 is -11, and 3, 0, 1, 0. Here we're just adding together, so 3 and 1 is 4, -4 and 0 is -4, and 1. And then our last row is just changing the signs. Okay, So again, this isn't anything new. This is just row operations. We've been doing this all term. So what do we notice here? This is the identity matrix. So that means this matrix is in fact invertible. If we did not have a pivot in every row / column, this is square, so that's the same thing, then this wouldn't be invertible. So if, for instance, this were a 0 down here, then we would know A isn't invertible and we wouldn't care what's on the other side. Since this is the identity matrix, A is invertible, and we do care what's on this side is going to give us our inverse. You can double check that if you multiply this inverse that we found by our original matrix A, you'll get the identity matrix back again. So to recap, inverses are our way of dealing with matrix division. Instead, we find an inverse, and then we multiply that inverse, and that undoes the matrix. Not every matrix is invertible. If we have a 2 by 2 matrix, we can easily check whether it's invertible by finding that 2 by 2 determinant, AD minus BC, and then find the formula for it. If our matrix is bigger than 2 by 2, we can take advantage of the fact that we can think of row operations as products of elementary matrices and just use this algorithm where we take our matrix, we augment on the appropriately sized identity, and row reduce down to find the inverse. All right, that's all I have for you today, and I will see you all in class.